Okay, welcome to Lesson 11 of Module 4. The title of this lesson is Constant Rates. And so we are going to continue looking at constant rates. In the last lesson, we talked about constant speed. Speed is just a specific type of rate, but there are others. So in this lesson, we'll kind of expand it to general constant rates. So we'll see some examples of that. So let's talk about what a rate is. So a rate is just a ratio with the two different measurements. So the numerator and the denominator will have different units of measurement that are being used. Okay, so there's your definition. So we could have something like cost per pound. Cost measured in dollars and, pounds, obviously pounds. We could have miles per hour as a rate, which is just speed. Or we could talk about something like a heart rate, which would be measured in number of beats per minute. So there's a number of types of rates that are not speed, okay? A ratio in general has the units of measurement are the same for the top and bottom. So for instance, if I wanted to look at a ratio of the number of oranges in a bowl to the number of apples, and I said there's 5 oranges for every 3 apples, that would be a ratio but not a rate. So that wouldn't count. And in this lesson, we're going to be talking about rates specifically that have time as one of the measurements. And it's always going to be something happening in a particular time interval. So some examples of that could be water flowing from a faucet and rates of work. So how fast does the carpet get laid or does the lawn get mowed? So both of those types of examples would have time as one of the measurements. So that's specifically what we're going to look at in this lesson. Okay, so let's get started with our first example. Okay, so let's look at example 1. It says Pauline mows a lawn at a constant rate. Suppose she mows a 35 square foot lawn in 2.5 minutes. What area in square feet can she mow in 10 minutes? Or in T minutes? Okay, so her average rate over the 2.5 minutes that she mowed was 35 square feet, and we're going to write that as feet squared, in 2.5 minutes. Okay, so that was her lawn mowing rate, and we're going to assume a constant rate in this problem. So first let's look at what area in square feet she can mow in 10 minutes. And so for the 10 minutes, we're going to let A stand for the area that she mows. Okay, so that's our variable. So the area mowed in 10 minutes is going to be A. And so we can set up her average rate for the 10 minutes, and we're going to call that A divided by 10 minutes. So it looks just like the one right above, right up here. But we know that because she's mowing at a constant rate, both of those average rates are the same. So the average rate over any time interval is going to be the same if it's a constant rate. So because of that, we're able to write a proportion and set those two fractions equal to one another. And so what we're going to be doing is cross multiplying those two rates, those ratios there. And so we can say that 35 times 10, which is 350, is equal to 2.5 times A. Okay, and so then I have an equation I can solve, divide both sides by 2.5, and I can see that it's 140 square feet that equals A. So Pauline mows 140 square feet in 10 minutes. Okay, so what we want to do now is we want to look at what is her rate for T minutes. So not just for a specific time period, but for any time period. And this is going to lead to an equation with two variables like we were doing in lesson 10. Okay, so the problem, we just found her area mode in 10 minutes. And so now we're going to go to a more general, as was asked in the problem, what area can she mow in t minutes? Okay, so we're going to let y, because we're going to be using an xy axis for these problems, x being the horizontal, y being the vertical. We're going to let y be the area mode, and we'll let t be time in minutes. So for any number of minutes, y will be the area mode. Okay, so we can write the rate for that would be the area over the time. So we can make our equation. I'm going to do it down below the table. So we would have, we know that 35 square feet in 2.5 minutes is her average rate over the 2.5 minutes. And because it's constant, we know that we can set that equal to just over any time interval. So if we have y being the area mode over t for time, the time for the y square feet, we can set up a general proportion. And so once again, we can cross multiply. Now we have two variables, so we won't be solving this for a particular number, but we're going to solve it for y. So this leads to 2.5 times y is equal to 35 times t. And if I go through and I want to solve for y, I could leave it like that, but it's handy to have these equations solved for y. I just want to divide by 2.5, and I get an equation that we can use for any amount of time that she mows. So y is equal to 35 over 2.5 times t. Okay, let me put parentheses around that. And so notice that this number here ends up being just her rate over the 2.5 minutes. So the area mode, y, is going to be equal to that, so this area mode, y, is going to be equal to her rate over the 2.5 minutes times whatever amount of time she mows for. Okay, so we can start to build a table. So what we want to do is we want to pick some different amounts of time, and our graph over here goes from 0 up to 7. So let's start with 0. So if she mows for 0 minutes, then the equation we're going to be solving here would be y is equal to 3.5, or not 3.5, sorry. I keep doing that. It's 35, because it was 35 square feet. 35 over 2.5 times t is 0, times t. So y is obviously 0. She doesn't mow at all. She doesn't get any lawn mowed. Okay, so we could do the same thing for 1. Again, plugging 1 into our equation here, into this equation, right here. Where are we? Yeah, this one, or more specifically, this one right here. This is our linear equation. So we're going to put 1 in there, and we're going to get an area in square feet. Okay. Okay, so for 1 minute, we can see that if we put in 1 for t, that we have the area in square feet is 14. So 35 divided by 2.5 is actually 14. So we could rewrite this equation a little simpler, and you can do it either way, but y is also equal to 14t. Okay, so we can use this simplified version. So let's do that for the rest of them. So we're going to do t for 2 minutes, 3 minutes, and 4 minutes. So y is equal to 14 times 2, or 28 square feet. And I'm not using units because it's in my table there, so it's square feet. For 3 minutes, y is equal to 14 times 3, which would be 42. And then y is equal to 14 times 4, which is 56. All right, so then I want to come over and I want to organize that on our graph. All right, so time in these types of rate problems, time is generally graphed on the x-axis. So we've got several points here that we can put on. So we have one at 0. Okay, so I've placed all of these points on the graph. So let's look at what we did here. So here's the point where time is 0 and lawn mowed is also 0. Okay, so moving over to time 1 minute, I can come up to my table, 14 square feet in 1 minute. So I'm going to come up here and place a dot right at 14. In 2 minutes, she could mow 28. In 3, she could mow 42, and in 4 minutes, she could mow 56 square feet. Okay, and so there's the graph that matches the table that matches our linear equation that we wrote. Okay, so you've done all of that. Okay, so that's example 1. Lawn mowing is a type of rate. Okay, so let's continue. Okay, so let's just restate a little bit. We are talking about constant rate, and we're using the term average rate, and we talked about this in the last lesson. Average rate is the rate over a certain time interval. So when we did the example of the person walking from one train station to another, her rate was not constant, but we could still calculate her average rate. Whereas the constant rate is something that occurs when the average rate is always the same, no matter what the time interval. So constant rate occurs when the average rate never changes. So, and we've said that it doesn't happen very often in real life, but often problems do occur where it is a reasonable assumption to make that the rate is not changing over a certain time period. So that's what we're going to be looking at. And like we said, each of these is going to be a different type of rate, and so we'll have to look at each problem individually. So we did average speed, or we did speed in the last lesson. Our first example was mowing a lawn, and so our next example has to do with water flowing out of a faucet. Okay, so example 2. Water flows at a constant rate out of a faucet. Suppose the volume of water that comes out in 3 minutes is 10.5 gallons. How many gallons of water comes out of the faucet in t minutes? So once again, we want to write an equation so that we can know for any amount of time, t minutes, the number of gallons. So we need variables for that. But first, before we do that, let's think about what type of units this rate is going to have. And as with these others that involve time, we always want our rate to be per a unit of time. So we're going to have gallons per minute. Gallons over minutes. Okay, so it's going to be gallons per minute. And so we can write our, well, let's define our variables first. So we're going to since we're working towards number of gallons in t minutes, we're going to let y be the number of gallons. And then we'll let t be the time, however much time elapses. So we can write some rates now. So we have, we know that 10.5 gallons flowed out of the faucet in 3 minutes. So that's a rate. And we can actually reduce this rate if we take 10.5 and divide it by 3. We can see that it's 3.5. So this is actually 3.5 gallons per minute. All right. And that is a rate. So we could use either one of these. We can use the fraction, or we can simplify it like this. So this is 3.5 gallons, and really what we have down here is a 1 for every 1 minute. Okay, so we have another rate though. We have the way we've defined our variables, we know that y gallons is going to leave the faucet in t minutes, and that's equal to a constant rate. And remember, we said that the other one was equal to a constant rate too. Okay, and since both of those average rates are the same because they're constant, we know that we can write that y over t is equal to 10.5 over 3. And that's going to lead to our cross multiplying and realizing that 3y is equal to 10.5t, and then dividing by 3 to get y by itself. We come up with our equation, and this is what we were looking for. So we know that y, the number of gallons, y, is equal to 10.5 over 3 times the time that the faucet is flowing. So that's our linear equation, and we could put it right there on your notes. Okay, so that's our general equation for the number of gallons that comes out in any number of minutes. Okay, so let's continue on. And we have here the table. So let's rewrite our equation. We had y is equal to 10.5 over 3 times t. And we have figured out that 10.5 over 3 is actually 3.5. But we can do it either way. So in 0 minutes, y is equal to 3.5 t. T is 0. Sorry, I meant to put that in. T is substituting 0 for t, so we'll have 0 gallons coming out. Okay, and then when it's 1, we have y is equal to 3.5 times 1, so we get 3.5, and so on. Y, and I should put up here, this is actually my y. They're calling it v here, but I called it y. 3.5 times 2, 7 gallons. 3.5 times 3 would be, here's our 10.5 coming up. 3 minutes. We already knew that point. Okay, and then in 4 minutes, we've got 3.5 times 4, which is 14 gallons. All right, now we can use this data and we're going to put it on our graph. And so on the horizontal axis, we have time in minutes, and on the vertical axis, we have volume of water in gallons. They called it V, I called it Y. Either way is fine. So we're going to plot these points. So at 0, in 0 minutes, 0 water flows out of the faucet. In 1 minute, we're going to have 3.5 gallons. Let's see if I can get this in the right place. Right about there. 3.5 gallons in 1 minute. In 2 minutes, we have 7. That would be right here. And then in 3 minutes, 10.5. In 4 minutes, we had 14. Minutes. Whoops. 14. Okay, so you can go ahead and plot those on your graph as well. And this is showing that every minute another 3.5 gallons of water flows out of the faucet. Okay, so as you look at this equation, hopefully you're getting used to seeing this number here as being the rate. That's the constant rate of flow of of water in this case. In the case of speed, this was the speed. But anyway, it's the rate, and it keeps popping up again and again. But we're using this proportion to create these equations. So, yeah. So anyway, let's do another example. This is starting to make more sense. Actually, I want to ask you a question about this graph. So if I had looked at this graph, using the graph, could you figure out how many gallons of water would flow after 1.5 minutes? Okay, and so what I could do is come over here to 1.5 minutes and estimate, somewhere right in there. So I would have to say that it would be somewhere between the 7 gallons that flow out in 2 minutes and the 3.5 that flow out in 1. So somewhere in between there. Okay. Likewise, what if I wanted to know how many gallons would flow out of the faucet, or how long would it take for 15 gallons to flow out of the faucet? So I could come up here to 15 on the graph, which it was not there, it's right here, and kind of follow that over, and realize that that it would have to be more than 4 minutes and probably less than 5. So somewhere between 4 and 5 minutes for 15 gallons to flow. Because in another minute, in 5 minutes, we're going to have another 3.5 gallons. So it'll be up here somewhere up there. So somewhere in here, between 4 and 5 minutes is where 15 gallons would flow out. Okay, so it's a really good skill to be able to look at a graph like this and tell some things about the physical situation. And a lot of times it's easier to do on a graph than it is to do with an equation or just doing the computation. So it's good to get used to using graphs in this way. All right, let's keep going. Okay, now that you've seen a couple examples, try to work on exercises 1 through 3 independently. As you finish them, you could restart the video and look for my solutions. The exercise 1 is typing rate, so it's going to be how many pages of text can he type in a number of minutes. And then 2 is Emily painting something. She's painting a wall, and she's painting at a constant rate. So she can paint a certain area in a certain number of minutes. And then exercise 3 is back to constant speed. So walking at a speed that is a certain number of miles in a given time interval of minutes. So work on those exercises 1 through 3. You might want to check yourself on them one at a time to make sure you know what's going on. Okay. Okay, so we are given that Juan types at a constant rate. He can type 1 full page of text in 3.5 minutes. And we want to know how many pages, and we're given the variable p, that Juan can type after t minutes. So we have a variable t. And so we want to write the linear equation first in 2 variables, p and t, that represents the number of pages Juan types at any given time. And so we have a rate that is a constant rate that that Juan can type 1 page in 3.5 minutes. So 1 over 3.5 is our constant rate. And we also know, using our variable, that he can type p pages in t minutes. And that's going to be equal to the same constant rate. And so once again, since the average rates are the same, and we have constant rate, we can write out these equations. So we can do the proportion, we can set it equal to, we can do the cross multiplication here and figure out that p is equal to 1 over 3.5 times t. And so that's our constant rate. And so what we want to do is for all these different times to see how many pages that Juan's going to type. And so we're just going to put in for t the numbers 0, 5, 10, 15, and 20, and see how many pages he can type in that amount of time. So notice the directions say to use a calculator and round your answers to the 10th place. And so we're rounding. And these are the number of pages. So in 20 minutes, Juan can type just shy of 6 pages of text. Okay, so once we've done this, now we're going to graph the data on the coordinate plane. So let's look at that. So in 0 minutes, he typed 0 pages, so we'll put 1 point there. Then we're going to move over to 5 minutes, which is right here, and we're going to plot 1.4. So he can do, in 5 minutes, he can type just over, about almost 1.5 pages. So right about there. In our next data point is 10 minutes. So we're looking at, we want to come right over here. There's 10 minutes. And we're going to go up to 2.9. So that's going to be right about there. just shy of 3. So I'll put it under like that. Okay, and then now our next data point is 15 minutes. And in 15 minutes, we found he could type 4.3 pages. So just over 4, somewhere right in there. Okay, so try to get in the right place. And then in 20 minutes, which is right here on the horizontal axis, he could type 5.7. So that's going to be just, let's see, this is 6. So in 20 minutes, just shy of 6 pages. Or a little less than that. It's hard to do this with the iPad. Nah, keeps going right on 6. Okay, closer. All right, so there's a graph of the data on the coordinate plane there. Okay, so we do have one more question, and part D, which I don't have on this screen, but you have it on your page. How long would it take Juan to type a 5-page paper? And so what we want to do is we want to come over here because the vertical axis is pages. So 5 pages is here. So I'm going to come over and realize that it's going to be somewhere in here. So it's going to be somewhere between 15 and 20 minutes for him to type a 5-page paper. Okay, so that's a way to use a graph to find a piece of data that we didn't calculate. Okay, so let's go on to exercise 2. And again, if you haven't done it yet, you should pause the video before you look at the answer. Okay. Okay, so here's the results for exercise 2. So we've got Emily painting at a constant rate. She can paint 32 square feet in 5 minutes. And so we want to know what area, A, in square feet can she paint in T minutes. So I've written up here, our rate is going to be in feet squared per minute. And the rate that we're given as a constant rate is 32 square feet in 5 minutes. And so that is our constant rate. And then using the variables that we're given A for area, T for time. And so we know that the area in a given amount of time is equal to C. And so we can set those two ratios equal to one another, A over T, 32 over 5. And looking at the cross products, we'll get that 5 times A is 32 times T, and dividing by 5, we get A is equal to 32 over 5 times T. So that's our linear equation in 2 variables that gives us for any amount of time we can figure out the area that Emily can paint. And so filling out the table, we're going to use a calculator and round our answers to the 10th place. And so we see that in 0 minutes she can paint 0 square feet, and in 1 minute she can paint 6.4, which is 32 divided by 5. And then so on, 12.8, 19.2, and 25.6. So those are the areas she can paint in 0, 1, 2, 3, or 4 minutes. Okay, so once again, we're going to put this data on a graph and see what that looks like. So we're just seeing lots and lots of proportional relationships in this lesson. So here's our graph, and we want to put the data that we calculated on this graph. And so once again, we have for 0 minutes she can paint 0 square feet. Surprise, surprise. And then each of our other data points is for 1, 2, 3, and 4 minutes. So let's get those on there. Okay, so I have plotted each of the points. So 0, 0. In 1 minute, she could go 6.4. So always make sure to look at the scale on a graph. So on this graph, they have labeled it by 2s, 2, 4, 6, 8, 10. Okay, so 6.4. In 2 minutes, we had 12.8. In 3 minutes, we went up to 19.2. And then in 4 minutes, we had 25.6. Okay, so let's see. If I don't think that point was really in the right place. 19.2. See, this is 20. There's 19. So somewhere right there. Yep, lower than that. All right, it's hard to do once again on this, but close enough. You get the idea. Okay, so now we're asked in part D, how many square feet can Emily paint in 2.5 minutes? Explain. Okay, so what I want to do is I realize that in 2 minutes she could paint 12.8, and in 3 minutes this is up to 19.2. So in 2.5 she's going to paint somewhere in this interval, right between there, about halfway. So without calculating it, we could say that it would be between 12.8 and 19.2. Okay. Okay, so exercise 3 is constant speed. Joseph walks at a constant speed. He walked to a store that is 1/2 mile away in 6 minutes. How many miles M can he walk in T minutes? So in general. So we do have these two variables. Miles is M and minutes is T. Okay. So we're going to write a linear equation in those two variables that represents the number of miles he can walk in any given time interval. Okay, so we have a constant speed, and we know that he can walk 1/2 of a mile, or 0.5 miles, in 6 minutes, and that's equal to our constant speed. And since we know it's constant over any time interval, he can go any number of miles M in T minutes, and that's also equal to C. Okay, so we can set those two equal because we have constant speed, and then solve for M, and we'll get M is 0.5 over 6 times T. Okay, I want to point out, and maybe you've noticed that sometimes you can simplify these ratios. So right over here, this ratio here, 1/2 a mile in 6 minutes, that would be equivalent to 1 mile in 12 minutes. So instead of this, we could use this slightly simpler ratio. But I went ahead with this because that's how we've been doing these. But know that you can simplify these, and that is fine as long as you understand what you're doing. Okay, so we can do that. Then I want to draw your attention down here too. Once again, distance equals rate times time. So distance is miles here. Rate is 0.5 miles in 6 minutes. And time is time. Okay, so these equations that we're coming up with, these rate equations, especially when it comes to speed, you can think in terms of this. This is really what we came up with just by looking at the proportions and ratios and figuring it out. So distance equals rate times time. Okay. Okay, so completing this table, you can use a calculator. Most of these you could do in your head though. We're rounding to the tens place, although we don't really need to round. So our linear equation is right here. It's m is equal to 0.5 over 6 times t. And we're going to use, for time, we're going to use 0, 30, 60, 90, and 120 minutes. And so we're going to see, obviously in 0 minutes, he can go 0 miles. And in 30 minutes, he can go 2.5 miles. In 60 minutes, 5 miles. In 90 minutes, he can go another 2.5 miles, or 7.5. And then in 120 minutes, or 2 hours, he can go 10 miles. Okay, so just putting in different values for t and then doing the calculation to find out what m is in miles. Okay, so what we want to do now is lastly we'll graph that on the coordinate plane. Okay, so your graph should look something like this. There's the point 0, 0. In 30 minutes, he walked 2.5 miles, so that's about right here. This is 2, 4, 6, 8, so this would be 3, about halfway, so that might be a little high, but right in the ballpark. In 60 minutes, he could go 5 miles, so right between the 4 and the 6. In 90 minutes, we're at 7.5, and at 120 minutes, we're at 10. So that is what those points look like on this coordinate plane. All right, so the last question says Joseph's friend lives 4 miles from him. How long would it take Joseph to walk to his friend's house? So if we come up on the vertical axis and find 4 and follow it over, you can see that the data point should be right in here. So if he, it would be between 30 and 60 minutes. So certainly less than an hour, because in an hour he can go 5 miles. So somewhere right in here. All right, so we have seen constant rate problems, and we've expressed each of these constant rate problems as a 2-variable equation. We were able to make a table and also make a graph by computing the data points from the equations that we wrote. Okay, so you should read the lesson summary, which is right here on your problem set page. Work the exit ticket and the problem set. You're going to need graph paper for these. You'll need to use a separate sheet of paper because there's not room here. Actually, looking at your problem set again, they give you coordinate graphs for all the graphs that you need to do, so you can do those right on the papers in your student handouts. Okay, good luck with that, and I'll see you back here for lesson 12.